Today we'll be going over designing rockets in OpenRocket and simulating their flights. OpenRocket is a fantastic resource whether you be a beginner or a experienced rocketeer, and I think that it's great to hop in and see how rockets fly and the whole shebang. It's great. So if we're going to start building a rocket, we'll start with our nose cone. Now, I'm not going to go through all the different types of nose cones. You can look that up, and they all have their own pros and cons based on how fast you'll be going, for how long, and all of that. There's a whole science to it. Usually, ogive, I still don't know how to say it, but this is usually a great bet. The shape parameter is really how well the nose cone forms into the body tube. So if we have a 1, it's going to be more rounded and go smoothly into the body tube. Whereas you see as we drag to lower to 0, it becomes more cone shaped. This really, in my experience, isn't great for the flight unless you're going some crazy specific speeds. I never have seen the use of a cone shaped nose cone over over something more rounded like this. Now, if we want to start modeling what we actually have, I know for a fact that my team, we don't roll our own nose cones. We usually will buy fiberglass nose cones from the internet. And so lots of this is known. So we just have to tell OpenRocket what we mean so we can start simulating that. So first of all, I said fiberglass. We are using fiberglass. This greatly affects the weight. You don't want to build a rocket without putting this weight in or this component material in, because not only does it affect the weight, but the rocket flies differently based on what you're putting in, and OpenRocket knows this. Now, I know for a fact that my nose cone is 24 inches long and 6 inches, or rather 6.007 inches in diameter. The wall thickness is going to be calculated usually, but there's all sorts of options. Now, your cone doesn't just sit on top of the body. It's got a shoulder. It slips in. So I know for a fact that my diameter is 5.5 for that shoulder, and I know that its length is 6. So you can see now we have this peg that can glide into the body tube as we go on it. Now, thickness, I hope, speaks for itself. I'm still learning about it, so if it doesn't speak for itself, don't worry about it. The mass, OpenRocket will do its best to calculate the correct mass. You see here 25.2 ounces, but no motors, which is just our nose cone. But if we know for a fact what our mass is, then we can go ahead and override that mass and put ours in. So I think mine is something like 22 ounces. So not a huge difference, but everything will add up at the end. So now we can start building the rest of our rocket. To separate your rocket, you need to separate for your parachutes to deploy. Usually we build our rockets like this. We'll have one smaller tube, we'll have a coupler, another tube, and then we'll add fins to this tube. So let's start putting in some normal lengths. We're not just shooting this a little bullet. So first of all, we can call this something like 18 inches. I know my team rolls our own tubes. So we can adjust this as we go, but many people will buy these tubes. When I say roll, we put carbon fiber on a aluminum mandrel and pump liquid nitrogen through the mandrel to shrink it so we can slide our carbon fiber off. So I said carbon fiber. Let's look for it. All right, here we go. Now here's where things get a little sticky. Our carbon fiber, we calculated the density, and for the tubes we roll, they're much lighter than this kind. It's much more accurate simulation if you weigh your own things, and I know that I said these are certain weights and measurements, but you really want to wait till you get the actual component, like actually get the nose cone to weigh it and make sure OpenRocket is really simulating to the best of its ability. So here, this isn't usually an OpenRocket, but you can customize your material. So I can go ahead and name something. I said ARA, standing for Alabama Rocketry Association carbon fiber, and then R, calculate density. And you can do this and then add whatever material you want. That's true with many things, at least in this application. So that's our upper tube. We have our outer diameter, and I'm not too sure if we specified this, but usually it will follow the lead of your nose cone. Now this component is not a motor mount, and the weight well, we just don't have a weight right now, so we're going to go ahead and let OpenRocket calculate that. I know that our tube coupler, well, we'll get to that after I make this. We can call our bottom tube the one that, your bottom tube usually will either hold the motor directly or hold the motor casing, which holds your motor for the rocket. And of course, we'll get to that as we go. So first of all, we'll go ahead and we'll change our component material to carbon fiber. We'll go ahead and change our length. We could call it something like 50 inches, maybe 47 inches. Yep, and that will be that. Now, when I was saying about your coupler, there's a lot of rules of thumbs in the rocket biz, and one of them is your coupler should be twice as long as your diameter. Many rules of thumbs are based on your diameter, and you'll see that with our fins too. You may see a trend starting to occur. We change we only use fiberglass and carbon fiber. They're strong and they get the job done. So we have a fiberglass coupler, right? So I'm changing my component material to fiberglass. We'll make our outer diameter, it needs to press against the wall, so that looks fine. We can have an inner diameter. Instead of doing that, I'll show you the calculation. This is going to be bad if it doesn't calculate. There you go. We can call our wall thickness a certain number, and then it will calculate the diameter. Same thing if we changed our diameter, it would calculate the wall thickness. And we said we wanted it twice as long as our diameter. So we have a 6-inch diameter rocket, so our length of our coupler will be 12. Now, it's not exactly between the two tubes, so we're going to have to move it 6 inches so that it's right in the middle of the two tubes. If you're wondering about how everything fits together, we generally will screw this nose cone in, or we put shear pins in it, and the coupler is just friction held right here. Alright, so we'll get to populating our rocket with all of our electronics and parachutes as we go. But right now we're just building the outer case. So we have all that's dandy. Now where does our motor go? Well, you know what? I said we're going to populate in a sec. So next up is our fins. The fins is where you can really play with the entire thing, play with your stabilities, and let's just hop right into it. So I like the trapezoidal. Freeform, you have a lot of authority. There's all sorts of science to these fins. Basically, you don't want them too big so that you would have so much drag, but you don't want them so small as to, give up control. You don't want little nubs like this. That would be terrible. This would be a terrible flight. The number of fins really doesn't matter. You could have 3 or 4 and it's going to fly the same. Your fin rotation is how off they are, and so it doesn't really make sense. You see, as I'm changing it, it doesn't make sense when we're just fine looking at them like this. The fin cant is how much it twists. So I'll change our cant, and then you can see from the back our fins are twisted. Now, why would you do this? Well, you would do this because some people like a flight where it intentionally twists it so that it makes it more stable, kind of like a Nerf football when you're throwing it through the air. We don't do that. Maybe we're in the wrong, but I know what's worked, and I've never seen that on a high altitude rocket, probably because of the stress it's put on the fins, especially during supersonic flight. So our root cord, when we say root cord, we mean the root of the fin, what's touching the body. All right. So like I said, lots of rules of thumb. And if I remember correctly, a great rule of thumb for your fins is your root cord you want 3 times as long as your body, and then your tip, and the tip kind of goes without saying. The tip is half of your root cord. I meant the tip goes without saying that it's the tip, but you have no way of knowing that that would be half the root cord. So we said 3 times the diameter. Let's go ahead and make it happen. Looks a little wanky, so let's go ahead and have that for our tip. Our height, another rule of thumb, you generally want your height the same as your diameter. So we have a 6-inch diameter. We'll make our height 6. Now they're kind of backwards right here. So your sweep length is how they're pushed back. So they're kind of pushed forward right here. So you could either change the angle or the length. Like many other things, it will calculate the other if you do one. So I like doing the length. So let's call it 10. And here you go. Nice and sweep back. And we have a sweep angle of 59 degrees. So you can play around with that. I generally like this look because, first of all, it looks great. But it also functions very well. It's pretty solid on drag. You never want your typical triangle fins because of the eddies of air that affect how it flies. So component material, you pretty much guessed it, fiberglass. We have carbon fiber tubes, and we have fiberglass accessories, if you'd like to call them that. All right, so we're getting a pretty solid rocket. Our stability is now something not horrendous, and you can start to see a trend. So something you have to keep in mind. You always want your center of pressure behind your center of gravity. If I could demonstrate this in some kind of experiment, I would, but I just have a screen. So what you should think about it as is, say well, I don't really have an analogy, but you always want this right behind the center of gravity. Now, this is going to change as we add propellant, as we fly, and then that's when you have to plan ahead with your eBay, what weights you have in the front, and all sorts of things. So we'll cover that. Well, a rocket's not a rocket without a motor. So let's go ahead and get to that. Now, there's two ways you can do it. You can make this entire tube your motor. For very big rockets, that's what they do. I know for a fact that USC has a minimum diameter 8-inch rocket, and it's all full of propellant. When I say minimum diameter, I mean this entire thing is full of propellant. But for most rockets, that's not the case. For most rockets, we just have a tube within it that holds our motor. So here we're adding our inner tube, and we could call this our motor case, because it is. We could call its outer diameter something not horrendous. It really depends on what kind of motor you're trying to fly with. Motors generally go from, on millimeters we usually talk about them as, but there's a pretty convenient conversion. If you want to convert your units in OpenRocket, you can go ahead and do that in the settings. I just like imperial units because I'm an American. Now, our component material, this can be anything. We can call it something like fiberglass because motor cases are built out of aluminum, fiberglass, carbon fiber, composite overwrap pressure vessels, the whole 9 yards. So we'll go ahead and give it our heavy carbon fiber, and we'll say its diameter is 3.96, which is 98 millimeters, or roughly 98 millimeters. We'll call its length something like, I don't know, 48.8 inches. That's not a guess. I actually have motors like that. And you see it's kind of interacting with our coupler here, so we're gonna have to fix that. So, but we have our outer diameter of 4, we have our inner diameter of 3.96. We need to tell OpenRocket, yes, we expect this to be a motor mount. If we want to cluster, there's all sorts of clustering configurations. Clustering's great when you don't have the certifications, or well, scratch that. I don't know if you still need certifications, but it's cheaper to get smaller motors and cluster them together. And all these things I really don't use, so I really can't talk about. All right. So I said we need to fix this up. It's pretty easy to fix the lengths and things like that. Much easier than something like SolidWorks. So we'll go ahead and make this 54 inches. All right. And one's 56. Okay. So now we have our motor mount. It's kind of floating here though, so we need a few things. First of all, this 56 actually won't even do. You're going to see in a second. All right, so we need a few things. First of all, it's not restrained, I guess, here vertically. We need something to hold it in place. It's also not constrained horizontally. We need some kind of block to stop that engine from moving forward. If only there was some kind of block to stop an engine from moving forward. We can add an engine block. Go figure. We'll put this at the end of it, so we'll call it, we'll say plus 49. Ooh, minus 49. All right. This is in relation to the end of the rocket, to the tip of the rocket. And here's our motor block right here. Engine block, whatever you want to call it. Usually it is something like aluminum, so I'll go ahead and call it aluminum. I'm still learning why it's so thick and what affects that, but you're pretty solid to say that its length could be 2. Just a block of aluminum that's bolted into this body is going to stop any motor coming forth. So we can go ahead and throw that in. If we have, like I said, every time you get the actual component, you should go ahead and override that mass. I don't know the actual mass, so we're going to trust OpenRocket's judgment. Now, we stopped it horizontally, but we still need it vertically. We use centering rings for this. Now, centering rings they can be anything you want. Go figure. I'm going to use fiberglass. They're like little donuts that you just slip your motor case through, and it just holds it steady. They really don't need to be anything fancy. You could probably do it with wood. But we can go ahead and say our inner diameter is 4, outer diameter is 5.85. OpenRocket was already ahead of us on that one. But we can definitely affect our thickness, which is pretty important. We can go ahead and do something like 0.25 inches thick. And here's our nice centering ring back here. Now we can go ahead and move this, copy it, whatever we want. So let's go ahead and call this our bottom ring. And let's go ahead and copy. Control C plus V, or Control, you know what I'm saying. Alright, we have middle, and we have our top. And so now all we got to do is do our pluses and minuses. So we'll do, in fact, since this is like our negative x-axis, we're always going to be going negative. So we're really going like negative 38. And so this is going to be our top ring. And then for our next one, we can go, for our middle one, we can say, all right, we want to go negative, got to do some quick maths, 19. And so we have them nicely spaced out, right? And so this will hold our motor when we inevitably put it in. Now, I know we're skirting around the motor, but I want to introduce this one concept really quick. It's called a boat tail. Now, a boat tail, you can see this little distance right here. It's going to get some eddies from the air. The form drag is really not going to like that, and it's really going to kill our altitude if we're trying to go high, right? So first of all, we want to prevent that, and boat tails do that. So there's not necessarily a button for a boat tail, but all it really is a transition. And here's what they look like. A boat tail, it basically just makes up for this little space between the outer diameter and the outer diameter, or the outer diameter of the rocket and the outer diameter of our motor casing. And so generally, conical is a good way to go. Our transition length, this will affect, your apogee, and it's a lot of things to play with. But we'll get to some tools that can help us later. The component really doesn't matter actually here. I like to use plastic because I can print pretty easily, but I don't believe I put plastic in here just yet. So like I said, it really doesn't matter. I'm going to go ahead and use something like birch. It really does not matter. And so I'll go ahead and call my transition length 6. We have our fore diameter and our aft diameter. Now, the aft diameter, you want to remember, it's fitting around our motor casing. So we need to match this diameter. So we'll go ahead and call it 4. Now, the stage is set for us to finally get our motor in. We have our airframe down, and it looks gorgeous. So let's go ahead and pick a motor. So we can start a new configuration, select a motor. Well, we have everything from 0 impulse, which there's no point to even having it, to something monstrous like a 41,000 to 41,000 total impulse. Now, if we just want our 3.86, oh, I hope I didn't say 3.96 earlier. Did I say 3.96 earlier? We're about to find out. I did. All right. Which means our centering rings are wrong. Oh, no, they're actually fine. Okay. So everything's fine. don't worry about it. So we go into our motor case, and OpenRocket knows we're trying to put a motor there. So we go ahead and we can select whatever motor we want. Now, each motor is different. Some are sold with just the grains. Some are sold with the cases. Maybe I'll do a later video about that because that's taken me a little bit to learn about. But we can go ahead and select whatever we want. So I personally like the N4800 because it is discontinued, but it's a monster of a motor. And so, yep, here we have us going to 79,000 feet. It's a monster of a motor relative to the others. In fact, the O3400's a true behemoth. So, we'll go with this. So, the way you design your rocket, it's always going to be dependent upon how fast you're going, how long you're going to be going that fast, all sorts of things. So, first of all, we want to pull our motor out into the boat tail so that we don't hit it. We're not spewing hot gases just to melt our boat tail or catch it on fire. Whatever it's made of, it's going to destroy it. So we can go ahead and say our motor case, we actually want plus 6 inches into the boat tail because the boat tail is 6 inches. And that actually reminds me, this engine block we'll have to say also plus 6 inches. All right. And now here we have elongated our rocket, but the form is much better. And we can go ahead and do some experiments to see, does a boat tail even really matter? And it does. OpenRocket takes into account all the aerodynamics of the whole rocket. It's a fantastic code. So you might be saying, hey, 794 feet is like nothing, and you said it was a monster of a motor. I did say it was a monster of a motor, and I may look stupid, but the stability is also -1. Now, I also said keep your CP behind your CG and it's in front. This thing is going to tumble right off the launch pad and it's not going to be pretty. So we have not done a few things. First of all, you're going to have electronics up here, maybe in your nose cone, maybe in your coupler. That's pretty much where they always are. You'll have parachutes in this middle tube, and you'll might not need all this room in this tube. So we can make some room for our parachutes in this tube by taking some room out of this tube. So let's go ahead and say, hey, we don't need all that length. We can drop down 4 inches. Maybe one more. All right. So with that 8 inches we drop down, we can go ahead and add that here. So now we have enough room for our parachutes. Stability still, actually the stability is way more atrocious. That's because we forgot our avionics. So in our avionics, we put an E-bay, and we put our electronics bay. And so here, we're going to add a mass component, some arbitrary component here, but rest assured, this is standing for all of our electronics. And so we're going to put it right in the middle of our nose cone. And depending on how much you have in there, the eBay is probably not going to be heavy enough to even offset this. So you may even need to throw in something like some weights. And this is a common practice. People put a lot of weight in the nose cone. And if you ever wondered why you always had to, make the front of your paper planes extra creased to increase the weight, and add a certain weight to your nose cones, if you've been doing this a while, this is why. You need to get that CG above that CP for a stable flight. So we can go ahead and say, all right, we have a heavy eBay at 10 pounds. Okay, things are looking a little bit better. In fact, our apogee just shot up. If you wanted to run the percentages, it's probably something unfathomable. 30, I don't know. I'm not going to try. 3,000%. So we have our mass up here, and if we want to really increase the stability, this is where the fun kind of begins, because you want these guys apart from each other so that your stability is between 1 and 2 the entire flight. It's great to start out with a great stability, but the big thing that people forget, when we take out this motor, which means after it's all burnt up, this is how stable we're going to be. Not too stable at all. And so you really need to plan for as the grain burns and how it's burning and all sorts of calculus that programs already do for us, how that's going to affect your flight. So we can do a few things. First of all, to pull back the CP, we can increase the amount of fins we have. And I actually skipped one thing over with these fins. I'll get to that in a sec. If we go up, we lose a bit of altitude, but our stability increases greatly because we were able to pull back our CP. And the same way, if we wanted to pull up our CG and get even more in the 10 range, we would just add more things up here. So I said we needed a parachute. Let's go ahead and add a parachute. We'll throw in a 6-foot diameter parachute. Parachutes really aren't that heavy, but they're pretty space consuming. So never doubt how much space a parachute is going to take up, because it's going to take up a solid amount. So you know, and you can get all of these things down when you actually have the parachute, but I really don't think a parachute needs all that much explaining. Now, you've probably seen throughout the video, we've given a lot of really useful information. Not only our stability right here, but we have our apogee, which is what we're really looking for. We also have our max velocity, Mach 1.94. Your big thing here, and we'll go over this with our flight simulations as we get closer to it, but you really want to stay out of transonic, but you know what? I'll cover that when we go over it. So you can add all sorts of things, but since we're just kind of breezing through it, you know, you really want to account for all these things when you're making a real rocket, simulating whatever work you're doing engineering-wise. A bulkhead would just be attached to the parachutes. A shock cord would be attached to the bulkhead, attached to the parachutes. A streamer is really just to look pretty. There's really no value to it other than helping you see it. And our launch lug goes along our pipe on the launch pad. Now, I know I breezed through all of that, but it's really best learned through doing, and I really encourage you to go actually launch a rocket. Now, I said I forgot something about our fins. Here, our fins, of course we glue them to the body tube, and we'll do certain processes to distribute the weight along the body tube. But the best thing about having a motor that's not minimum diameter, meaning the motor doesn't take up the entire outer body, is we can actually attach our fins directly to the motor tube, which means the real root of them is not on the outside, it's on the inside, and those things aren't coming off at all. And so we can do that manually. This is what a fin tab is. We can do that manually, or we can have OpenRocket calculated automatically. Sometimes it's right. Here, it is right. Sometimes it's wrong. We'll give it a pass. So now we have our fins with their tabs connected directly to our motor casing. And so things are looking pretty solid. We have our parachute accounted for. If we could move this a little bit, that would also be great. But if we can't in time for me to not make it, okay, we can move our parachute. Now, oftentimes you'll have drogue chutes. You'll have that in addition to this main chute. But certain teams only use main chutes, especially depending on where you're launching from, and that's perfectly fine. So we'll go ahead and call it even with our main chute. So, isn't this a beautiful rocket? We can look at it from the side view, from the back view, making sure everything's straight. It has no reason to not be. And let's go run it through some simulations. So we take our configuration. If you want to compare other motors, especially from this drop-down menu, you can go ahead and make new configurations and rename them and do whatever you want. So we'll call this bad boy our high altitude. It's an O motor, meaning, well, they're rated on their impulse. I guess we could go over that right now. So when we say something is a K or an O, here you go, or any of the others, they only have O on OpenRocket, but you can add more. We won't do that today, though. This is really just saying this impulse falls in a certain range. And if it's in a certain range, so M, we can call the range anything from 5,322 to 10,369, we'll call an M. But of course those two aren't equal, so when we say it's an M, we'll say, it's really a 98% M, which means it's barely an M, it's almost an N. In the same way, if we go really far back to right when it turns an M, to right when it turns an M, it's only 4% M. So you can see as we go through, you can see our M's change as it becomes more and more of an M and less of an M after we get over 50. All right, so you've also probably noticed this thrust curve. Now, this is dependent upon how you cut the grain, which we'll see in open motor or burn sim or whatever. But the most thrust isn't really all you want all the time. If you get right off the pad just absolutely blazing, you may kill your rocket because you're going, Mach 4 with some horrendous acceleration so low in the atmosphere that everything rips apart and you don't get anything back. Well, you do get your rocket back, but you get 30 pieces of it. So we're not going to do that. We can actually see the entire simulation or the entire flight simulation if we run it through here. We can plot it, and here you go. We have our motor burnout right here, which makes sense because our vertical velocity starts to drop off right after we burn out. We have our acceleration skyrockets, no pun intended, then we burn out, and then it gets almost jutted back all the way back here because the air, after it burnt out, it was going so fast, and now the air kind of has its revenge and pushes us back. And then we're rolling steady. And so here we go to apogee, our highest point in the flight, clearly, as indicated by our red line, and then it's a nice cruise down until we hit the ground. Now it's important to know you want to hit the ground pretty softly. There's all sorts of rules of thumb, and they're pretty easy calculations for your parachute and how big it would be. But, generally 20 feet per second and lower, you'd be fine. All right, so we can export that data. We can look at it. We can add different types of events, new plot types. We could say total velocity, lateral distance, air pressure. All of these things are fantastic if you're trying to develop, new technologies like maybe an aerospike or maybe some cool payload or all sorts of things. We're not going to do that. We're just looking for altitude. We're speed demons here. And so that's pretty much the gist of it. Now there are some pretty cool tools for OpenRocket. We have an optimization tool. I believe this is off the screen for you guys, but you should look up in your top bar. You'll have tools. And here you go. And we have rocket optimization. And so what we can do here is we can take any component we want and we say, hey, our fins are pretty solid, but do we know that they're really the best? And so we can go ahead and say, hey, I'm going to go to my fin set and I'm going to test if my height's really the best it can be, if my sweep is really the best it can be, and we'll even say our chords, and we can start our optimization. Now, sometimes it gets pretty atrocious with this. OpenRocket is not perfect, but we can reset that. And here, this isn't asking all that much, and hey, we tacked on 1,000 feet or so we can go ahead and apply that optimization. And we're looking at a better designed rocket that we use the tool for. And I think that this is the most fun part because you can go through everything and optimize it. You can go ahead and say, hey, I don't know if our boat tail is really the best length for what we're trying to do. And so we're going for altitude. But you can also do other things. You can say, how hard you're hitting the ground, like what we were just talking about with our parachutes and all sorts of things. And so we said, is this length really the best? We'll go ahead and optimize it. And it could have been slightly better at 6.037 inches. So that's pretty much the basics of building a rocket. I hope you guys get out there and simulate whatever you're flying, whether it be your L1, L2, some high-powered rocket for your university, some high-powered rocket because you feel like it, or some Estes rocket. It works for all of them, and I will see you in the next video.